Hello everyone, my name is Geeta and I want to start with a quick introduction about myself. I'm a machine learning scientist and engineer slash researcher, and I work on developing, training and deploying machine learning models into production at large scale real world system with a good part of my experience in FANG companies. I've spent a significant part of my career working on deep learning models, large scale data, and production systems. And today, we are going to talk about something that sits at the core of almost every modern AI system you hear about, the transformers. The title of today's session is Transformer Anatomy from Tokenization to Self Attention. By the end of this session, my hope and goal is for you to just recognize transformer architecture, but actually to understand what each block is doing and why does it even. Before we go into the details of this talk, I want to generally talk about like my assumptions. I'm first assuming that you are comfortable with Python and you have some high level exposure to machine learning. You don't necessarily need to know the math in detail, but concepts like models, training, and inference shouldn't completely be new. Today, the agenda for me is to break down the building blocks of a transformer model. We'll start from the very beginning, tokenization, and then move step by step through embeddings, self-attention, and finally the encoder and decoder architecture. My focus here is just to get some intuition to understand what problem each block is solving. After that, we'll move forward with a live code walkthrough and we'll connect these concepts directly to code so that you can see how theory maps into implementation. By the end, I want you to feel confident looking at the transformer diagrams, the architectures in recent LLM papers or work, and including code, and understand how they fit together. Alright, now that we've got some basics out of the way, let's open up the transformer and start with the very first question. How does raw text even become something a model can understand? Well, for that, we need to understand what is tokenization. So this is where everything in a transformer begins. At its core, tokenization is a process of converting raw text into discrete units called tokens. These tokens can be words, subwords, or even individual characters, depending on the tokenizer being used. The key idea here is simple but extremely important. Neural networks cannot understand raw text. They only operate on numbers. So before we can apply any of the advanced deep learning magic, we first need a way to break language into pieces that can be mapped into numbers. Tokenization allows the model to process language in small digestible units rather than treating the entire sentence as a single object. In modern production models like BERT, GPT, T5, we usually rely on subword tokenization, the most recent one being byte pair encoding and the variants. This helps strike a balance between words being efficiently handled to represent rare words or completely new terms or even languages. Tokenizers typically operate on a fixed vocabulary, and that vocabulary is the size of some thousands of tokens, typically like 30 to 50,000 tokens. And every token in this vocabulary is assigned a unique integer ID. And from this point onward, after the tokenization, the model only ever sees sequences of IDs. So now that we've mapped it to a number and that numerical sequence becomes the model's input, we move on to the next step, token embeddings. At this stage, the model is working with integer IDs, and integers by themselves don't carry too much meaning. For example, token ID 127 is not inherently closer to 128 than it is to 9000. These are numbers and they are just labels. So the next critical step is to convert each token ID into a vector representation that has some meaning in terms of closeness and so on. This is done using like various methods, mostly learned embeddings or rotary embeddings and so on. The purpose is to get into a high dimensional space to allow encoding of rich semantic information. I think over the course of this training, we'll learn on how like these semantic embeddings come into picture for the models. Typically in embeddings world, let's say I want to give a example, like a very usual analogy, like words like king and queen or run and running will have like embedding vectors that are closer together than totally unrelated words. So now we moved on from token IDs to vector representation. If you can visualize this, you can think of token embeddings as turning the one-dimensional list of token IDs into like a matrix where each row is a token and column is a learned representation feature. Now let's move on to the next thing, which is positional encoding. And basically, unlike RNNs, the recurrent neural networks, or like long short term memory units or the GRUs, transformers process all tokens in parallel. So this parallelism is one of the biggest reasons that transformers are fast and scalable, but it does come with a trade-off. They do not have any notion of sequence order because we are processing them in parallel. To fix this, we introduced what is called the positional encoding. The positional encodings are vectors that inject information about the token's position in the sequence directly into the embedding. The key idea is we add a positional encoder or positional encodings, which in the original transformer model are generated using sinusoidal functions. For example, positional encoding of a position and dimension equals to the sine of the position divided by this mathy 10,000 raised to the power 2i over d. So although we don't need to memorize this formula, the important intuition is that each position gets a unique smooth pattern across dimensions, and this is how we are encoding positional information that now the transformer understands. Why are we actually talking about transformers, and why is this paradigm shift? I guess I want to touch upon this briefly before going into self-attention. It is important to pause and understand why transformers was such a major breakthrough in the first place. To do that, let's briefly compare like recurrent neural networks, RNNs, with transformers. Looking at transformers, RNNs process tokens one by one, sequentially, and they suffer from vanishing gradient problems with long sequences. That means, let's say we have the cat in the beginning of the program, in the paragraph, and we are trying to refer to the cat at the end of the paragraph. That information from the earlier tokens tends to fade away as the sequence gets longer and longer. Another major limitation is that RNNs cannot be parallelized effectively because it's sequential in nature and very slow in training. As a result, RNNs struggle with training speed and modeling long contexts. Now let's go on to transformers. Transformer process all the tokens simultaneously in parallel. There is no step-by-step recurrence. Instead, every token it can directly interact with every other token via what we call the attention mechanism, which we are going to discuss in the next slide. This design completely avoids the traditional vanishing gradient issues seen in deep recurrent networks. Because computation is highly parallelizable, transformers train much faster at scale, especially on GPUs and TPUs. And most importantly, self-attention allows transformers to model long-range dependencies extremely well, even across tens of thousands or more tokens in modern systems. This shift from sequential recurrence to parallel attention is the core reason transformers replaced RNNs and became the foundation for today's large language models. Okay, next I actually want to dive into the heart of transformer architecture, the self-attention mechanism. It is a key idea that allows every token in the sequence to look at other tokens and decide what matters and why. Even though I have a slide here, I feel that it's best illustrated through illustrations, and I find like this illustration from J. Alomar. Like I will have this website up for whoever, the link for whoever is interested. But the illustrator transformer has one of the nicest illustrations to understand this in like detail. Okay, we'll first look at how self-attention works at the level of individual vectors and then connect it to matrix multiplication and so on. So essentially what we are starting with is, in this case, like input, like thinking machine is the example that is used. Now we are like, the first step is converting them into embeddings. We talked about it roughly, and now each word in the sentence, we take its embedding vector here x1 and transform it into three different vectors: query, key, and value. Importantly, these vectors are not like magically created, but they are produced by multiplying the embedding by their weight matrices WQ, WK, and WV. At this point, everybody might be wondering, what are these queries, keys, and values, and why should we care? Think about them as like learned abstractions that can help the model decide what to look for, what information is available, and what information is we are able to extract. At this point, we don't need to assign hard meanings, and we'll understand it better once we understand the math a little bit and maybe code later on. I'll just try to come back to it again and again. So let's talk about the computation. Suppose we are computing self-attention for the first word in the sentence. For example, thinking. We are taking the query vector for this word q1 and we compute the dot product with the key vector for every word in the sentence. So q1 dot k1 and q1 dot k2. So these scores represent how relevant each word is to the current word that we are encoding. Basically, we have the dot product q1, k1, and then we divide it by the dimensionality, square root of the dimensionality of the key vector. That's what is represented here as square root of dk, and then we softmax it. So basically, this component comes out to be 0.88 because softmax makes it a probability distribution. So this should sum up to 1, and we got here 0.88 and 0.12, and now we have these scores which will be multiplied by the value vectors that we have. So, and these are our new attention weights for the value vectors. The next thing is a mechanism called multi-headed attention. This improves the performance of attention layer in two ways. One is we are trying to focus on different aspects of the sentence, and that's what is meant by representation subspecies and so on. So the way that we do it is by having multiple heads. So instead of having like one set of query key value vectors, we have several of these query key value vectors, and these are our attention heads, so to say, from 0 to let's say 8 and so on. And we do the same self attention calculation for each attention head, okay, in this case from 0, 1, 2, 3 until 7. And in the end we concatenate the input of all the attention heads and multiply with the weight matrix that we've trained to get our Z matrix that captures information from all the attention. So putting it all in one visual here, basically we are starting from our sentence thinking machine, and we embed each word in our matrix X. Then we split into multiple heads, you can see from 0 until 7, and we calculate the attention using the QKV matrices and the calculation that we've seen before, and concatenate the results to get the Z matrix, which we multiply with the output matrix to get the output of the layer. So essentially what it is saying is, let's say we have a long sentence like this: the animal didn't cross the street because it was too tired. So now when we say it, you can see here which words it is referring to. It is more strongly referring to the animal. So that's what attention is trying to get from each of the token and this self-attention mechanisms. Now, after we've spoken about the core concept of self-attention and multi-head attention, now let's zoom out and look at how these pieces come together inside a transformer block. So transformer model isn't just one attention layer. It's built by stacking many of the transformer blocks one on top of the other. But within each transformer block, it has the same internal structure. So each transformer block starts with an input embedding, which has the token information and the positional information already, and these are passed into the first sublayer of the block. And before so I guess layer norm where it is placed depends upon the model and LLM we are talking about. We've been doing pre-norm, post-norm and so on. But let's say here I'm talking about we first apply layer normalization. The reason why we have this is for stabilizing training by ensuring that the input to each sublayer has consistent scale. Most modern transformers use this pre-norm structure where normalization happens before the main operation. Next, we apply the multi-head self-attention. This is the communication step of the transformer, and this is what we've talked about it at length. The next layer that we have is add a norm step. Basically what we are doing is we are adding a residual connection and add it back to the original input, and then we apply normalization again. The residual connections are critical because they allow the gradients to flow through deep networks and make training stable even with many stacked layers. Otherwise we have the problem of vanishing gradients and so on. Residual connections are like one method to make sure we can make like deep networks without collapse. Next, we need feed forward networks. This is typically like a small neural network with two layers and non-linearity that is applied independently to each token. This is followed by another add norm, again like with the residual connections, and finally this goes into the output of the block. So this is like the entire transformer block. Let's see if I have an image in the next slide. Okay, here I have it. So basically, yeah, the input embedding with the sinusoidal positional embedding, the multi-head attention. Here you can see in the architecture, this is the residual connection going through the add and norm layers, following through the feed forward and the add and norm layers. This entire block on the left, this is called the encoder, and this entire this entire block on the right is called decoder. This picture is from the original transformer paper, here you can't see it in the image here, sorry, my poor editing. We have the original transformer has six of these blocks, the transformer blocks processing inputs in parallel, and 6 decoder transformer blocks generating output tokens sequentially. And we have the cross, the decoder differs from the encoders in a sense that we also have cross attention, where decoder attends to the encoder outputs as well for context, and there is also causal masking. So basically, let's talk a little bit of about like causal masking and cross attention. Those are the two new things in decoder. To make a sequential generation process possible, the decoder uses what we call causal masking. This ensures that the token in the decoder cannot attend to future tokens. It only looks at tokens to its left, the previous tokens. In other words, when predicting the next word, the model is only allowed to look at previously generated tokens and never the future one. This is what, when people are calling decoders and autoregressive models, this is what they mean by that. The next thing which I've mentioned about is cross attention. In addition to mass self attention, the decoder uses this component called this cross attention, which allows the decoder to attend to encoder's input. This is how the decoder gets access to the input context, right? Like, because we have like the input prompt, or let's say input whatever that we were giving to the transformer, and the decoder gets access to the input context directly. Okay, now let's summarize it. Now that we've looked at all the blocks, the encoder basically reads and understands the input sequence in parallel, and the decoder generates the output sequence step by step. Cross attention is the one that is connecting the two, allowing the decoder to use encoder context, and causal masking ensures autoregressive behavior. This encoder decoder structure is the foundation for many modern models, even though some there are variants. In the earlier years we had mostly encoder only variants like BERT and other Roberta, and a lot of encoder variants, and there are some like GPT which are decoder only variants. Most of the modern generative applications are decoder variants. Okay, now we've covered the basics. I guess I really want to end with the note on the impact and evolution. So that the first paper, the transformer paper, came out in 2017 with a paper called Attention is All You Need. And this paper introduced the original transformer architecture and showed for the first time that attention alone was sufficient to model sequences without using recurrence or convolution. What started as an architectural experiment quickly became a foundational shift in how we build models today. In 2018, BERT GPT came about, but what they brought to the world is pre-training breakthrough. As you can imagine, these models have large size and they are extremely data hungry, and preparing labeled data like we typically do in supervised learning is very hard. And these models for the first time introduced large scale pre-training on massive text corpora, that and then it is followed by fine tuning for downstream tasks. This changed the field like entirely, from training the models from scratch before this time frame to actually training once and adapting to many tasks. And in 2020 is when like GPT-3 and few short learning came about. Like GPT-3, I think with like few billion parameters, demonstrated that models could perform few shot, zero shot, simply by conditioning on prompts. This is the moment when transformer transition from research systems to general purpose like reasoning engines. And 2024 and beyond, like I guess like fast forward, modern language models are routinely exceed like 100 billion parameters. They are no longer text models. They are multimodal, capable of understanding a lot of context. They can power systems, chatbots for many applications. They didn't like improve just the performance, but they unified AI in a lot of ways. So I think this is all because of transformers and its architecture. Even though we touched upon like language models up until now, it has its implications on vision transformers, speech recognition, multimodal agents, and so on. And transformer has become the dominant building block of modern AI. So now this is why I spent so much time on why transformers matter, how they work, how they evolved. And now for the next 10-15 minutes, we need to make this concrete. We are going to walk through an actual demo code to see how these ideas, tokenization, embedding, attention, and transformer blocks show up in practice. Let's open up a notebook and build our intuition with code. But I want to get into the code for like how like we do scale dot product attention. Like we touched briefly in the slides, but if you remember, what we've done is a matrix multiplication of q and k vectors, and then we scaled it, and then we did a softmax, and then we did a matrix multiplication with module. So this is exactly what we are trying to replicate here. So all we are doing is, okay, we are getting the dimension of the k vector. Okay, this is the size of the key, and then we are doing a matrix multiplication of query key, and then scaling it by the dimension. And the next step, if you remember, is a softmax. So we do a softmax of these scores, and then these weights we multiply with the value vector. just like it here. After softmax, we just do the matrix multiplication with value vector. So that's as simple as it is. That's our scale dot product attention. Now I'm just like putting it in in a class so that we have it available. As I've mentioned to you, these are just projections of the input vectors and the weight vectors. So that's what we've done here, and this is where we used our scale dot product attention that we've written in this cell, and we return the attention outputs, the weights multiplied by the value. And the next thing, if you remember, we talked about is multi-head attention. So multi-head attention is essentially we're trying to get like different representations in different subspaces, right? So what we are doing here is, let's say we have a model dimension, and we decided architecturally that we want to have 8 heads or 4 heads. Then the head dimension will be based on model dimension by the number of heads. That's the head dimension. And what we are doing here is just a for loop. We're just saying, okay, I have my attention head, I'm just creating like n heads, like based on the number of heads, and then we are getting the output, right? And what we are doing in the forward layer is concatenation of all of those, as we've seen in the theory section. And once we get the output, we do like a concatenation, and we send it to the output layer, and that's our final output. Feed forward layer here has nothing too much special. As I've mentioned, a couple of linear layers as you've seen here. So it's like NN dot linear with basically the hidden size and the intermediate size, and the activation that we use is GELU, and we typically use some dropout, and this is how we're going to have our inputs in feed forward. Basically we have a linear activation, and then the linear and the output dropout layers. Now we talked about feed forward, we talked about multi-head attention, right? And the next thing, now we're going to talk about having this transformer encoder layer. If you look at the image here, you see a multi-head attention, layer norms, feed forward, layer norms, right? So that is exactly what we are defining here. Okay, let me scroll down. That is what we are defining here. So we have in the transformer encoder layer, we are defining the layer norms, and then the attention and the feed forward. And if you see how we are forwarding, we are doing the layer norm of the input, the X first, and then attention on top of it. This is not the same as here. I have prenorm here, unlike the postnorm implemented, because this is most common these days. We do prenorm. So that's basically it. Like we have layer normalization, attention, and this is the residual addition, like basically where we are adding the X directly. If you see in the figure, like we are just adding X directly, right? So that is what the residual connection that we've talked in the theory. So this is what it is. We are adding X directly and to the attention output. And the next thing that we are doing is passing the this X to the second layer norm feed forward with the residual connection, and this is our transformer encoder layer, right? Okay, now embeddings is the first thing that we touched on. Basically, if you remember, what we said is we get the token embeddings, we get the position embeddings, and we have layer norms dropouts. So essentially what we are doing here is the input that we are passing to the layer norm and so on is the embedding. And what is this embedding? This embedding is token embedding plus the position embedding, right? And this is what we are sending to our model, and these are our embeddings. Just for consistency's sake, we generally do layer norm for smoother training and dropout, so that we don't overfit and so on. So this is our embeddings block. So now we've defined the encoder layer, we've defined the embeddings. So now the transformer encoder is now very straightforward. It's basically we start with the embeddings, and then we configured this encoder layer. We just pass the embeddings. The next layers the next layers are transformer encoder layers. So what we are doing in forward, as you can see, is X goes through this embedding. Yeah, so we get the embeddings out, right? And then we pass on to all the layers of transformer encoders that we've defined. So here essentially what I'm trying to do is, like, I copied the config that is there in one of the checkpoint. So if the checkpoint says okay, the number of hidden layers or the transformer encoder layers are, let's say, 6 or 12, it just copies the number from there, and we are trying to replicate it and say that we have the same architecture and so on. And that's our transformer encoder. So typically this is something that I've mentioned also briefly in the theory talk. Basically, for sequence classification, what we do is we add like a classifier on top of what we have learned so far after pre-training, and this is for specific tasks. This is how we define it. So everything the same, nothing special. The transformer encoder with dropout, and the classifier is just a linear layer. Okay, the one last thing, like the code in the architecture I want to touch about is decoder, and like what is different in the decoder. Essentially, okay, sorry, I'm just okay. So what is different is, if you see the scale dot product attention, the thing that needs to be different is, if you remember, masking. We shouldn't be looking at the future. So that's what this is doing. Basically, we do a mask here, torch.trill or torch.trio. What it's doing is, the upper diagonal, we are making it basically infinity, so that it is masked, right? Because we are saying whenever there is a mask, fill it to infinity, and then we do softmax on top of it, so the model is not able to look at tokens to the right. So that's the major difference in decoder. Other than that, implementation wise, everything is as we discussed. Now this is just, I showed you the the architecture just so that it maps to the theory that we have discussed so far, but in practice, we don't need to be coding things from scratch for doing any kind of model development. Even in FANG companies, what we work with many times is picking off the shelf models that have best performance on certain tasks. let's say I'm working on a translational task, and you look at benchmarks that are available, and let's say at that specific point in time, T5 is a better performing model for that task. So you pick off the shelf model based on the best baseline that is available at the time. And it's very simple to pick the model. Like as I've said, once you install like the basic libraries like the transformers from Hugging Face, all it takes is we figure out which checkpoint, and we load the tokenizers and the model on the checkpoint. And here I'm just demonstrating with the data set that is publicly available, and this particular data set is called like Samsung. You can just see like what the data set is about. So basically it is a dialogue of Adam saying what do you think, and Hector saying give me a second, and they are just talking about conversing back and forth and so on, right? And so here I'm talking about like fine tuning like this dialogue back and forth, so we can train the model on summarization. So I have some basic functions here, these methods also, there are some blanket examples in Hugging Face. So let me actually just open Hugging Face. So I want to just also you to just get familiar with Hugging Face. This is a lot of they have lot of open source models and so on. So let's say we go to T5. I'm searching for T5. There are a lot of versions of T5 small. Let's say T5 small. Okay, so let's go to the official one. This is Google T5 small. So now it has all the model card, the information and so on, training details, how they are trained and whatnot, the data sets that it has been trained on, like all the information is available. And let's say, where does it have information on? Yeah, it has model details. And then let me see if I can quickly find how to get started with the model. This is what we want to look at. We essentially want to see, why don't I see it? Okay, use the code below. I have to click on use the code below. So if you see here, okay, this it gives like a starter code on how you can use the model, load the model and how to get the outputs from the last hidden state and whatnot. Online they also sometimes have like good notebooks and blogs within Hugging Face on how to use it for summarizing task, or like classification task, or a tagging task, or a entity recognition task, or some generative task and whatnot. So basically what we need is processing, this is all text data, right? And we need to process the inputs. So we have to define like a pre-processing function which says, here you are actually doing some kind of prompting. We are saying summarize this, right? And then we are giving all the things in the dialogue, and then we are just saying we are sending the inputs to the tokenizer, right? And then those are our model inputs. Okay, and this pre-process function, so its job is to get the raw text and give model inputs. So we define a preprocessor, and Here, like, we didn't necessarily touch so much on compute metrics, so I don't want to go into this here. But generally what we are saying is, uh, we want to give, like, some metrics for the model to just give us a notion of, is it improving or not with the training, right? So that's the reason why we define some metrics, and we give them as like arguments to train. So we define the, this is how we start training the model. We say, like, I am giving you a model checkpoint with these arguments, right? And the tokenized training data set and eval data set is the processed data set that we've generated here, the tokenized train, validation, and test. This is the data set that we are sending as an argument, right? And the other parameters that we are discussing, like, if you know of any modeling, we have to talk about, like, like how many batches, like how many samples in each batch, how many epochs that you want to train, and whatnot, right? So give those hyperparameters, we set the trainer up, and then just say train. And then right now I don't have, like, it is still training. I wanted to show you how to actually fine tune with, like, picking a off the shelf transformer model or any model. So here I'm not, like, necessarily like training a LLM, so I don't have, like, efficient fine-tuning methods here. I just want to show, like, a bare bones of how do you pick up a off-the-shelf model, like, just do some pre-processing of, like, some data set using the tokenizer, and then just start to train. This summarizes what I want to talk about in this lecture. Hopefully this is all, like, starting to make sense. And even though we covered a lot of details, this is mostly for, like, understanding intuition. Like, sometimes when the model makes mistakes, the intuition generally helps on why it cannot, like, necessarily count R's in strawberry and whatnot, because we have to remember the basics, that we have to go back to tokens and whatnot, and, like, self attention also, right? So how are long range, like, dependencies handled, and like, what does compute mean, what is all this computation, inference, the sequential and parallel processing, and so on. So that's the high level intuition I want to, like, give in this session. Hopefully all of this is starting to make some sense, and I really enjoyed, like, talking about this, and I hope you had like, some fun trying to look through this. And I'll share the resources, and I, like, please come back to me if you have any questions. That's it for this talk, and thank you.